HVAC Energy Saving Optimization. Welcome, and thank you for joining today's session on HVAC Energy Saving Optimization. In this presentation, we will explore how to enhance HVAC system efficiency, reduce energy consumption, and lower operational costs while maintaining peak performance. We will cover various strategies, such as managing variable loads, utilizing variable speed drives, optimizing system designs, and leveraging innovative technologies like direct digital controls and energy recovery methods. Efficiency. Efficiency in a system depends on both the performance of individual equipment and how effectively the system is designed and used. Even if equipment is efficient, the overall system can be inefficient if the equipment is not properly utilized or integrated into the system. Management often has differing views on efficiency, with purchasing managers typically focused on minimizing upfront costs by choosing cheaper equipment, while chief engineers are more concerned with long-term operational costs such as energy consumption, maintenance, and utility expenses. A successful system requires balancing both initial investment and long-term operational efficiency to ensure sustainable performance. Dealing with variable loads. Dealing with variable loads is crucial in HVAC systems, as these systems must adapt to fluctuating conditions throughout the day, week, and year. Over a 24-hour period, a hotel system encounters different temperature and humidity levels during the night and day, which can vary significantly. Over a week, the hotel's occupancy might change due to factors like off-peak days or seasonal shifts, and seasonal changes can significantly impact the HVAC load throughout the year. To manage these variations efficiently, two key factors are essential. First, the selection of the equipment and system design should be based on life cycle costs, ensuring long-term operational efficiency, and second, effective system management during operation to adjust for changing loads and maintain performance. Variable speed drives. Variable speed drives can significantly improve efficiency in HVAC systems by adjusting the speed of motors based on load requirements. For example, in a chiller system, a variable speed drive allows the chiller to produce more cold water during times of heavy load and less during lighter loads, while maintaining the same water temperature. This helps optimize energy use by producing only the necessary amount of chilled water. When more water circulates through the cooling coils, it absorbs heat from the air more effectively, leading to better overall cooling. These efficiency gains are controlled through advanced logic and configuration in systems like building management systems or Internet of Things modules, ensuring the system operates optimally based on real-time conditions. This image explains the differences between primary, constant flow, and secondary, variable flow, pumping systems in HVAC systems. The primary pumps circulate water through the main distribution piping, while the secondary pumps distribute the water to individual zones or air handling units. The secondary pumps operate at variable speeds to match the changing demand, providing energy savings compared to constant speed primary pumps. The diagram shows the basic layout of the two types of pumping systems and how they work together to efficiently move the water through the HVAC system. This image depicts the primary-secondary rule of flow for HVAC systems. The diagram shows the primary and secondary pumping loops, and the text states that the primary flow must always be equal to or greater than the secondary flow. This rule ensures that the primary system has sufficient capacity to meet the demands of the secondary system, preventing backflow or imbalances in the system. Adhering to this primary-secondary rule of flow is an important principle for designing and operating efficient and effective HVAC systems. This image depicts the configuration and operating conditions of a 100% load scenario in a chilled water system. It shows the primary and secondary pumping loops, with the primary pumps operating at a constant flow rate of 720 GPM and the secondary pumps operating at a variable flow rate to meet the system's cooling demands. The image also provides the specific equipment details, such as the chiller tonnage, temperature differentials, and the required flow rate at the secondary side. This image depicts the configuration and operating conditions of a 75% load scenario in a chilled water system. The primary pumps are operating at a constant flow rate of 540 GPM, while the secondary pumps are operating at a variable flow rate to meet the reduced cooling demands. The image provides the specific equipment details, such as the chiller tonnage and temperature differentials, as well as the required flow rate at the secondary side, which should be 540 GPM at the required head. This image depicts the configuration and operating conditions of a 50% load scenario in a chilled water system. The primary pumps are operating at a constant flow rate of 360 GPM, while the secondary pumps are operating at a variable flow rate to meet the reduced cooling demands. The image provides the specific equipment details, such as the chiller tonnage and temperature differentials, as well as the required flow rate at the secondary side, which should be 360 GPM at the required head. The system also shows a switch-off notation, indicating that under this 50% load condition, one of the primary pumps can be turned off to save energy. This image depicts the configuration and operating conditions of a 25% load scenario in a chilled water system. The primary pumps are operating at a constant flow rate of 180 GPM, while the secondary pumps are operating at a variable flow rate to meet the reduced cooling demands. The image provides the specific equipment details, such as the chiller tonnage and temperature differentials, as well as the required flow rate at the secondary side, which should be 180 GPM at the required head. The system also shows a switch-off notation, indicating that under this 25% load condition, two of the primary pumps can be turned off to save energy. In HVAC systems, the primary, constant flow, or secondary, variable flow, configuration has its own set of advantages and disadvantages. One of the main advantages is that it is easy to control and commission, making the system simpler to set up and manage. However, there are several disadvantages. Firstly, higher pump energy costs compared to variable primary flow systems occur because the pumps run continuously at full capacity, regardless of demand. Another drawback is the higher plant energy loss caused by a low delta T temperature difference, which reduces the overall efficiency of the system. Cooling towers. Cooling towers are highly effective in enhancing the performance of refrigeration systems. At full load, a typical cooling tower can cool the closed-circuit fluid, water or refrigerant, by 30 to 35 degrees Fahrenheit more than an air-cooled coil, significantly improving the overall efficiency of the refrigeration system. Some cooling towers are equipped with axial fans to boost airflow, but inefficiencies can arise from swirling air patterns. A simple solution to this problem is using an inexpensive hub seal disc, which can improve fan performance by 5 to 8%. Let's focus on maintenance, a vital practice to maintain the efficiency and ensure optimal performance of refrigeration systems. One key task is to purge air from the refrigerant if necessary. When air gets trapped in the refrigerant loop, it increases the compressor discharge pressure, leading to higher energy consumption. Some chillers have automatic air purgers equipped with meters that monitor running time, helping track whether air is being purged efficiently. Monitoring the running time daily or weekly can also help detect leaks that allow air into the system. Additionally, maintaining the refrigerant level is essential for optimal performance. This can be checked by observing the refrigerant sight glass and monitoring superheat and subcooling temperature readings. Let's continue with maintenance. Effective maintenance is essential for optimizing the performance and longevity of refrigeration systems. One critical task is to minimize scale and fouling by using the appropriate water treatment for the chilled and condenser water loops. For systems that operate year-round, the degree of scaling can be monitored by checking the pressure drop and comparing it to the manufacturer's specifications. It's also important to maintain condensate drains to ensure proper drainage and system function. Some chillers are equipped with controls to manage capacity variations, such as unloading the chiller during periods of low demand. Direct digital controls. Direct digital controls offer a variety of methods to optimize HVAC system performance and efficiency by taking advantage of outdoor conditions and precisely controlling indoor space conditions. Examples include nighttime setbacks, where temperatures are adjusted during off-peak hours, demand-controlled airflow using occupancy or CO2 sensors, and optimized start-by-stop operations for fans and pumps based on system needs. Even in retrofit situations, direct digital controls can provide significant benefits. These concepts will be explored in detail in the BMS by IoT training module. Let's explore energy recovery, a continuation of strategies to enhance HVAC efficiency by reclaiming heat from various sources. One method involves heat recovery for hot water using a plate and frame heat exchanger, which captures heat from the condenser to produce hot water. Another option is using heat pipes, which efficiently transfer heat between spaces. Exhaust air energy recovery can be achieved with a heat wheel or energy recovery ventilator. In this system, the exhaust and incoming airflows are arranged side by side, each flowing through half of the wheel. The wheel is filled with a material that absorbs sensible or total heat from the outgoing airflow. Exhaust air. In HVAC systems, a central exhaust system is typically used to vent air from restrooms, kitchens, and janitorial closets directly outside, preventing it from mixing with the fresh air entering the building. The draft system that drives the central exhaust should be interlocked with the air conditioning or heat pump unit to ensure coordinated operation, except during unoccupied periods. This interlock helps optimize energy efficiency by ensuring that both systems work together. Motorized dampers are crucial in these systems. They open and close with the operation of the fan to control airflow. The damper should be placed as close as possible to the duct penetration of the building envelope to minimize conductive heat transfer through the duct wall, reducing the need for insulation. Let's understand hydronic balancing, a critical process for water-based systems to ensure proper water distribution through pipes, valves, and heat exchangers. In an ideally designed system, each component receives exactly the required flow. However, in practice, it's difficult to predict real flows, leading to some circuits receiving too much water and others not enough. Typically, circuits closer to the pumps tend to receive more flow. Balancing the system involves measuring these flows and adjusting them to the required values to ensure efficiency. The system uses differential pressure controllers and balancing valves to regulate these flows. Let's continue hydronic balancing, emphasizing that without proper balancing, control valves may reduce flow in overfed circuits while underfed circuits struggle to receive adequate flow. However, during peak demand periods, such as winter heating or summer cooling, the control valves may open fully, leading to some circuits still being underfed. Hydronic balancing ensures the system is evenly distributed, preventing some zones from being underheated or undercooled while others remain comfortable. This balance not only optimizes the indoor climate but also saves energy by reducing the pump's workload. With a balanced system, a smaller pump may be sufficient, and the system won't need to start earlier or run longer, as is the case with unbalanced systems. Let's discuss optimizing free cooling with an economizer, a method that leverages outdoor air to effectively reduce energy usage. Instead of always minimizing the intake of outdoor air, there are times when it is beneficial to maximize outdoor air. An airside economizer helps save energy by using cool outside air to lower indoor temperatures. When the enthalpy, a measure of heat content, of the outside air is lower than that of the air inside the building, it is more energy efficient to bring in outdoor air for cooling. This process optimizes energy use by leveraging cooler outdoor air when available and adjusting based on real-time conditions. Let's look at pipes and ducts, essential components in distributing heating and cooling throughout the building in an HVAC system. For effective energy delivery, HVAC pipes and ducts must be in good condition and properly insulated to prevent energy loss to unintended areas. This helps ensure that the energy reaches the intended spaces without unnecessary waste. In industrial settings, process pipes and ducts can also contribute to the load on the HVAC system, affecting overall energy use. To minimize this impact, it is essential that these pipes and ducts are well insulated, both to reduce additional energy consumption by the HVAC system and to optimize the energy efficiency of the industrial process itself. Thank you for joining this session on HVAC energy saving optimization. We hope the strategies and insights shared today empower you to enhance your HVAC system's efficiency, reduce energy consumption, and achieve cost savings while maintaining optimal performance. In our next class, we will learn about HVAC commissioning.